Okay, ladies and gentlemen, today is even hotter than yesterday. I'm getting tired, so I try to be a little bit slower this time. Today we will talk about standing tunneling spectroscopy again, but we add a degree of freedom of spin, which we neglected in the first two talks. And that means we will have to look at ferromagnets, antiferromagnets, maybe also unconventional superconductors, which are close to antiferromagnetic phases. Then I will look at disordered superconductors. Okay, they don't have spin, but in some cases we have localized spins in them. And topological superconductors. We will see. This is not. I think the GFI chain has not been discussed yet. So, anyhow. So last time we looked at the principles of inelastic tunneling spectroscopy. That is, there are two parts of the total current, an elastic and an inelastic. They don't interfere. So if we take a constant local density of states, the first derivative of the tunneling current is a constant for the elastic one, and the inelastic one is an onset of a certain energy, phonon energy, and it looks like a step, or the second derivative then only contains peaks and dips symmetric around Fermi energy, which have the energy of the phonon and the peak height of the matrix element squares, or the scattering process. And you can also look at that from a different point of view. If you take a naked electron, it's not really naked, but it's already renormalized due to the potential in which it sits and electron-electron interaction, but now you also put the phonons, so this naked electron will be dressed with phonons and changes its mass and also lifetimes. It also contains the information about electron-phonon scattering. And then this picture, this inelastic tunneling, is actually just elastic tunneling due to this modified ratio of the electrons, the spectral density. Which brought us to the enlightenment that inelastic tunneling has to do with the linear spread functions, and then maybe we can measure it. And I showed you examples. And I cheated a little bit there because I renormalized the electrons, but I didn't renormalize the phonons. But typically there is a big theory that they are pretty separate. Okay, the electrons become superconducting, but the phonons do not change too much from going from normal to a superconducting state. This will be completely different now, later, for the unconventional superconductors. Then we look at vortices and Pauli-Legend states. I showed you some unpublished data on two-band superconductors, which were not inelastic, and I showed you really very new data that maybe we can also map phonons by their inelastic signature if they are in a box. So what's on the menu for today? We want to extend STM to a spin polarized version. So we want to measure also the spin. And this is complicated because in the STM experiment we have one quantity to measure, that's the current, and it contains information about the density, and we also want to get information about the spin polarization, so we have to play tricks. And then we extend our inelastic picture to magnetic excitations. This can be magnons, spin flips, paramagnons, antiferromagnetic magnons. And take the same steps that we did for phonon, inelastic phonon, scattering and superconductivity. Now we do with magnons and unconventional superconductors. Let's maybe other dispute this step. It's not clear what unconventional superconductivity actually is. Maybe it's non-phonon mediated. I don't know what the good definition is. Some people believe it's magnons, so I belong to that fraction. So I will interpret it that way. And a short excursion to disordered superconductor, and time allows some critical remarks about topologically topological superconductors from the experimental point of view. So what is spin polarized tunneling? Now, spin polarized tunneling actually is a surprisingly old phenomenon by this guy, Julia. And it's a single author paper, and it was a PhD thesis of this guy. And it was like 10 years before the giant magnetic resistance effect, which got the Nobel Prize. And that's basically the same thing, two magnets separated in tunneling, of course, by an insulator, and a GMR is a metal, non-magnetic metal, and you ask what is the conductance across this device. And this early experiment showed that there is a difference of this conduction if the two magnets are magnetized in the same direction or opposite direction. And this difference is about, in this early publication, it's 15%. So the tunneling current changes when we go from parallel to anti-parallel magnetization. And this can be interpreted very simply. We have the spin polarized density of states now on both sides, and we take again a Bartolin theory, but now for two channels. And during tunneling, of course, in vacuum, nothing can happen to the spin of the electron. And if you have a well-behaved insulator, also the spin of the electron during tunneling is conserved. So spin-hole interaction is small. Then, if the two electrons are parallel, I go from majority states to majority states. So this is called density of states. Majority is more of these defined from magnetization, but the density states that the Fermi energy actually is small. So we go from the small one to the small one, and from minority electrons, which have a large density at the Fermi edge, to a large one. And you remember that these currents are proportional to the density of states of both electrodes. And then you get two-component conductivity in the up channel and the down channel. Just something like this. But if you reverse now one of the electrodes, the magnetization, majority and minority spin character exchange, essentially. But the electron spin is conserved, so I go from these minority states to these majority states, from these majority states to minority. So it's like G up down plus G down up. And tunneling itself, the electron in this area is not spin sensitive. Yeah? It's just they have to go through a vacuum area. But in this case, we have, let's say, we name the density of states and up A and down B. So parallel configuration of current will be proportional of the conductivity is equal to proportional to something like A times A plus B times B. And if we have anti-parallel configuration, is equal to A plus A. And if A is not B, this is the triangular inequality, and A squared plus B squared is equal to larger than AB. So we get a larger current when the magnetizations are parallel. And this was first experimentally realized by Wulf in this paper, and he used chromium, an antiferromagnet, and he used a tungsten tip, and went here with constant current over these atomic states. Now the density of states does not matter. It does not care what's the direction of the local magnetization. It's the same density, but just the spin is in a different direction. So you get just, the tip will follow just the topography of this problem. But if you use a very high spin polarized tip, chromium dioxide is almost 100% spin polarized, and he repeated the experiment, he saw a small step, large step, small step, large step. So this is here. Why? If they are anti-parallel, the current is smaller, or conductivity is smaller, the tip will actually go a little bit closer to the surface to obtain the same tunneling current. And if the two magnetizations are parallel, the conductance is higher, the tip is a little bit contracted over the polarized tip position, and then there's a small step here, and a step up, and a large step here. So mixed into the topography is spin information. But in principle, you cannot tell if the steps are different in height or if there's spin polarization. Both cannot be distinguished. So actually, this spin polarization had rest for some time until 1998, when Matthias Bode had a very nice idea. So we want to separate spin and density. So why not do tunneling spectroscopy now with the spin polarized tip? And we go to the Terse-Hamann model, constant density of states in the tip, but spin polarized. So we have minority and majority in different concentration density of states. Our sample is just spin polarized. So again, we tunnel from green to green and red to red. So I have to take this red curve and this green curve, add them up and weight them by this density of states. So the green curve is not small intensity, the red curve is large intensity. Larger than the neck curve. And the anti-parallel configuration is now turning from green to red to green. So now the other curve, green one, will be weighted more than the red curve, and you see the difference in the spectrum. Yeah?
And how you create polarization inside the tip?
Ah, you take just a magnetic tip.
Ah, okay.
But I will show you examples. So that means with the additional variation of the energy, the IV, and you choose peaks which are spin polarized in the density of states, then by the peak height, you can decide if you are parallel or anti-parallel.
Sorry, still.
Yes?
Like magnetic tip, you mean just put it into a strong magnetic field?
No, magnetic material. Spin polarized emissions.
Okay, so with but it still should be metal, right?
Yeah.
Okay.
Maybe I should say that if you look at the current is the unpolarized current times 1 plus P1 equals theta P1 and P2 are the spin polarization. So 0 means unpolarized, 1 means fully majority, minus 1 fully minority polarized. Both on theta is the angle between the radio stations, or the spin polarization vectors if you like. So I give you an example from my group in 2004. We took an iron whisker. So iron whisker is a single crystal of iron, and one or more direction is the axis. All of the other surfaces are also one or more surfaces. And since they are long and very soft magnetic, they split up into 2 domains typically, or 4 domains actually. So the stray field is reduced by this, and there's a cap here, okay, then we clamp the sample. So we distorted the lattice, which causes a problem, but you can park your tip here and here, a magnetic tip, and without changing anything, just go from this domain to that domain, you can see the difference in the tunneling current. And we call it a differential conductivity, and there is actually a minority surface state in iron at around 1.1 electron volts, and you see that for parallel, we get a large surface state peak, which is spin polarized, and anti-parallel, a weak one. So this you can map. Yeah.
I didn't exactly get this set up. So you take literally a thin, let's say a thin wire of iron.
So our tip actually is a tungsten tip that we coat a little bit with iron. So
what tip?
It's a normal tungsten tip, and then we deposit some iron atoms into the tip. A film, let's say 5-6 monolayers, and then this film is ferromagnetic and is at the end of the tip. You could also take a bulk ferromagnet, or for that matter, you can also take an anti-ferromagnet, which is also spin polarized. Yeah.
Could you please talk a little bit louder?
Yes, I try to.
Also, the question. So you were to actually rotate the sample to check for the polarizer.
No, here we didn't. We go with it here and there, just laterally.
Okay.
This is easy. Yeah, I can laterally move. I cannot rotate this. Yeah. That is difficult.
Yeah.
So this is why we chose this particular example. And with an optical microscope, we just look at it, and then you use some circular polarized light, and this curve effect, you can see the optical image. This is an optical image, and you can see the magnetization in this optical microscope, and then you take the tip part here, take the tip part there.
Okay, so you already know what is the correlation direction, but
there, I see this actually on my video screen, and then comes the tip, and then I put the tip here and on there.
yeah, exactly.
Yeah. You can also apply a magnetic field and reverse the magnetization of the magnet. So you have a magnetic tip here, and your surface, and the current here is still polarized. What you don't like, usually, is to use a biferromagnet, because a biferromagnet is a magnetic straight field. So this would act on the magnetization configuration of this high. So this straight field is about half of the saturation magnetization of the material. So iron will give you, roughly speaking, a Tesla of magnetic straight field. And that's not really good, because maybe it moves the magnetic domains you want to image. So you can alternatively use an antiferromagnetic tip. Now this is no net magnetic moment, but the last atom, of course, has to be either one sublattice or the other sublattice of the antiferromagnet, so it's still polarized the current. And there is basically what only counts is the last atom. So in both of these images, the last atom is the green atom, so they give the same images in principle. And this is a work from Roland Wiesenganger's team in 2002. They took a small iron crystal. This was done by molecular beam epitaxy. And then you see, to reduce the magnetic stray field, the magnetization will make this vortex state. And in some direction, your tip is pointing, maybe to the right. Magnetization is pointing to the right, so here we get a large differential conductivity, here minimal. And if they are orthogonal, you get an intermediate one. But here, yeah.
Maybe I don't understand something, but we can just imagine a situation where I have, let's say, non-magnetic material with long spin relaxation time, and then when I first inject somehow electrons which are spin polarized, and then I bring this tip, which is non-magnetic, so no problems with magnetization whatsoever, to my sample, and seems a bit more like a divorce to problems. Where there's a flow is this kind of approach.
Well, to put the tip takes half an hour. I don't think that there's slit lifetimes in your samples within half an hour. So I can polarize. There are experiments actually like this. A very simple one, you take gallium arsenide and you strain the gallium arsenide, so then you have this heavy hole and light hole that's split off, and then if you pump with circular polarized light, you get relatively large polarization conduction band. And if you switch off the laser, there is no spin polarization. So actually you can, by light switch on and off, the spin polarization of gallium arsenide. This works. This has been done in Japan. The only problem is you have to shine the light here into the tunnel junction. And this is a ferromagnet, and the ferromagnet also has different absorption coefficient for left and right circular light. So your light intensity will also vary just because the sample absorbs it differently. So it's very hard to separate photoconductors from spin conductors.
Let me put it this way: if I take a normal tip
Yep.
and inject spin polarized electrons, how fast they will lose the spin polarization?
Depends on the energy of the electrons. It's usually what is called the Gilbert damping, and the damping is, let's say, typically good materials, a couple of percent of the energy. So the damping is a couple of percent of the energy. That means if you have an energy of a milli-electron volt, then the time is like 0.01 milli-electron volt. So this is, I don't know, somewhere in the picosecond range. So they don't live long.
Okay. Okay. Thank you.
Okay, so this is an antiferromagnetic, so you can actually measure the center of this vortex core pretty precisely. If you would try to do that with a ferromagnet, the stray field would move this object.
The scale there is 10 nanometers, the bar.
that bar is 10 nanometers.
So it's very good resolution.
Oh, it's atomic, I will show you. It's like STM. We also did something, since we had talked about frustration, I switched to frustration now. We grew samples like this. This is antiferromagnet, manganese, on iron. It's a layer-wise antiferromagnet, and let's say manganese couples ferromagnetically to iron. So that means if I see a step edge, I go from even to an odd number of layers on top of the iron, I should see a contrast, spin contrast. But iron is not flat. All of the crystals always have steps. So let's assume there's a step here. So this one is ferromagnetically, and this one is ferromagnetically iron. But here the first layer touches the second layer. You cannot, you have to frustrate the system. There's a transition region here due to frustration of the competing exchange interaction, and an antiferromagnetic domain will form. Luckily, iron and manganese atoms are not same size, so these kind of buried steps show up in topography. And, okay. I don't know if you can see that. So these are atomic steps of the manganese. This is N and N minus 1 layers, go from bright to dark. So this is the antiferromagnetic layers. But there's this kind of weak contrast, which is this buried step. And we expect a domain wall here, and indeed, this roughly the same height, but you also go from even to odd numbers of layers, and you see this frustration here in the antiferromagnet. So we can image domain walls and antiferromagnet. And the resolution now is even better, so this is pretty sharp. How far does this go? And I give you again an example from our group. There are other groups that have done this also. Again, with a frustrated system, again, manganese, this time silver, but it's a hexagonal lattice. We take silver, 1, 1, 1. So as you certainly can know, triangular lattice with antiferromagnetic coupling, I say this is up, this is down, don't forget. Yeah, so it cannot be up, it cannot be down. One of them is not satisfied. This is a frustrated system. And you can classically say what is the compromise. That is like this, like you have one between the neighboring space. So if you construct this unit cell, that's this one. One of the possible unit cells. I plot these magnetization vectors, so each neighbor has 190 degrees. Okay, there are many solutions for this. In principle, you can rotate all of the vectors together by an arbitrary angle, and it stays the same exchange interaction. But you notice that the unit cell now, this is the one atom unit cell, and this is the magnetic unit cell. And if we have a tip, for example, shows magnetization in this direction, parallel, 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 and these are nearly anti-parallel, so these atoms appear bright and those darker. Or if one tip is magnetized, for example, in this direction, then you see that this one will be brighter, some of them intermediate, and some of them anti-parallel, almost anti-parallel. So this is the experiment. We have silver and manganese, and this is the upward silver step. So, silver, silver, manganese here. It's hexagonal, and you can see the potential of STM. So we can see every silver atom in the STM image. It's a wave function of the silver atoms. We see every manganese atom in topography, and they are slightly different heights, so we can see this contrast between manganese and silver. Now we do the spin polarized STM, so this microscopy, we map this. Silver is unpolarized, has some kind of differential conductivity, and the manganese, you see, gets a new size of unit cell, which is this unit cell here. So we actually see that indeed this is the 120-degree Nagel state. This is the first image of any Nagel state in this case. At that time, it was a big thing. Yeah.
Does it mean that there is an atomic scale resolution on this?
Yeah. All of the essays are atomic resolution. If you are having the good tip and a good day, you see every atom. Sure, we see the wave functions of the Bloch states. They have maxima around the atoms.
Is there a way to change tip magnetic polarization?
Yes. So this would be a simple thing. This is an antiferromagnet. It will not react to external magnetic fields, but the tip, you can choose a ferromagnet, and then you apply a magnetic field, and then your tip magnetization will follow your external magnetization in magnetic field, but the antiferromagnet change is unchanged. That's the simplest way, or you pulse the tip, you will change the tip configuration by chance. You have a glass atom which now points into a different direction. Actually, I have examples where we exactly did that. In a different way, let's say we have a structure which is not four-fold symmetric, so we have two versions of it on the sample, and your tip of spin polarization is like this, so you can go from this domain to another domain, and then you measure the second component of the spin polarization, and you can plot vectors. We've done that, but I didn't want to bother you about that. So it's possible it has been done. So we can see the electron density, and with the trick of spin polarized STM, we can, if we have very strongly spin polarized states in the sample, we can go to the energy and resolve this thing.
Just to make sure I understood the concept correctly.
Yeah.
So, in the second picture, what you do is you consider the difference in signals between tip that's polarized in this direction and this direction, and because you know that you're searching for AFM pattern for near ordering, you will expect bumps in the material where there is such polarization, and this bump has particular texture, and in still where there's no texture whatsoever, that's why it's just a uniform background.
Yeah, so here is principally the situation of unpolarized tip, which is the square of the electron wave function. And here we also see the square of the electron wave function, separately if spin up, spin down, and weighted by the tip polarization.
So B is a difference between the two polarizations, or is
this is the direct image.
So it's particular polarization. Okay.
Yeah, particular. There are also techniques, actually, I wrote a patent on that, to change the spin polarization of the tip. These are special tips, very soft magnetic. Show it to the front. I all skip that before. So we make a tip like that. To audience it. What? That's a former. There's a tip. And you have a coil here, and magnetization is either this way or the opposite way. Switching from one to the other, you need only to apply more current here. Then you can actually measure the difference between those two orientations, and then you get a complete separation of density of states. But it's a little bit difficult, this technique, so it has to. We were the only group on the planet. So, the spectroscopic method I showed you is easier.
So, just to make sure that I understand things correctly, when you say that you measure polarization, you mean the difference in density of states of spins polarized in one direction and another direction, right? I mean, in the end of the day, you still measure the density of states, but for different spins. You don't measure like the magnetization itself, like with, I don't know, like with squeeze.
There is no magnetization. You measure spin polarization.
Yeah.
I'm sorry in my language.
Yes, sorry.
Very often we say magnetization, but in principle it's all spin polarization.
Yes, and still.
But for normal materials, the spin polarization is collinear with the magnetization. So you have maximally a minus sign. Yes. Okay. You got me? Okay, then we continue. How about magnetic excitations? Now I present you a very simple experiment. It's a thought experiment, but it has been done also in my group. We take an electron beam and hit it on the surface. And the surface is a magnet. And our electron beam is spin polarized. So there's one channel which is non-spin flip. I get scattering of my electrons from the surface, into momentum transfer, energy transfer, by phonons or whatever, but the spin is not changed. So this has nothing to do with magnetism. We have no phonons actually, only scattering and reflection. So it's like non-spin flip in neutron scattering. But there are spin flip processes. So let's say I come with a minority electron, I hit my surface. I can undergo exchange scattering. That means I kick out a majority electron, and a minority electron enters the first. Or you can think about just an exchange of this electron with the ferromagnet. So this means I come with a minority and I go out with a majority. I have reduced the total spin of my object, my sample, by 1 inch bar. Now the spin is totally conserved in all of this. The total spin is conserved. No spin-Hawking interaction. So this means if there's an energy in momentum transfer, this is carried away by this magnet. On the other hand, if I come with a majority electron and I go out with a minority electron, I increase the total spin of my object, my sample, by 1 inch bar. And this is the annihilation of my object. And the scattering process is the exchange interaction. That's one of this flying electron and one electron in the sample, and there's this non-flip and this two spin flip processes by this raising and lowering operators. So these are the spin selection rules. And I show you the experiment. So this is data on minority electrons hitting the surface, and we just check what's the energy of the reflected electron. So zero energy loss is the specular reflected electron without interaction, too much interaction. And most of the electrons, but some electrons are actually reduced in energy, as the energy loss here. And I can vary the direction of my detector. So I collect these electrons here, angular resolved, so I can change the momentum transfer just like a neutron scattering. And you see the state dispersions. This is a very low temperatures. So the inverse process, the annihilation of the magma, is unlikely because there are no thermal magnets. So we don't see this feature in the other switcher. So we know this excitation has a 1 inch bar and is only reducing the magnetization. This is a magnet.
How to move in which direction this electron?
Okay. The electron is created by photoemission of gallium arsenide with circular polarizing light. So the circular polarization of the light is in the direction of light flying speed. And the other spin is given by the magnetization of the sound. I can apply magnetic field and saturate the sound in either of the two directions in parallel and it's not a full experiment. It's not necessary to also measure the spin of the reflected. What counts is for selection rules, if you can create or not create magnets, if you come with a minority or majority electron. Yes, so minority electron means this spin polarization is opposite to the spin polarization of the average spin polarization of the sample, and this is the current. Yeah, my spins in the sample are a simple picture, all pointing in one direction, and if I come with a majority or a minority electron, we get a different result. So can this be done also in SDF? And I worked on that and we were overtaken by Andreas Heinrich at that time. He did a very nice experiment. Manganese atoms on a thin oxide. So this manganese atom sits on an oxide layer. This is a substrate. And the bare oxide, you see the IB flat on the manganese atom at P equals 0 flat. But if you apply a magnetic field, you see these steps. And the steps actually move with the magnetic field. And if you take, say, the middle point here, evaluate how it shifts as a G factor of 2. So what happens here is I have this single atom. I apply an electric field, I split my states. And if I do exchange scattering, I can go from here to here. And this is inelastic. This is only possible if my tunneling electron has the necessary energy. This is one step here, this is the upward step in the IDE, and this is inelastic tunneling spectroscopy. Now on the spin flip of a single atom.
I apologize, it was too fast for
Yeah.
me. So pictures A and B, they correspond to magnetically polarized STMs,
No,
or is it just
not
topography?
There's no spin polarization.
So what's happening in pictures A and B?
A is before manganese, this is after manganese deposition.
And-
now you have this manganese.
And this color plot corresponds to
And now you do tunneling spectroscopy via IDD on the oxide, this one, and on the manganese atom on the oxide, these two. This is for B equals 0, and this is for B equals 7.
Right.
So at B equals 0, I can do a spin flip without cost. So my step will be at 0 energy. You can't see it here, because with 0 energy, you step up in both directions.
The X is energy.
Oh yes, it's lost.
But
And
and
this is
sorry, a little louder. Sorry.
yes, this is the energy.
Okay.
The bias voltage 0 is here. This was somehow cut on my image. But here you can see it again, millivolts. And we take this to the positive side. At 0, there is nothing. 0 magnetic field. At 8 Tesla, there is the middle of the step is at 200 millielectron volts. You go to 7 Tesla, the middle of the step is at 8 millielectron volts. And this is exactly the Zeeman energy for this G factor 2. Change the manganese spin by 1 H bar. Okay, the manganese doesn't have spin 1 half, it has 5 half, but okay, doesn't matter. The Zeeman spectrum is the same. Okay. So we can excite the spin of a system, in this case against the Zeeman energy, by a spin flip event. And it's just like a step up in the formats, like it's inelastic energy that we transfer to the system. So maybe clearer in this picture, we come with a minority electron, it's scattered to a majority electron. This one will leave the sample on the backside of the tip, if you like, of the sample, and we reduce the magnetization by 1 H bar from the emission of a magnet. So this is tunneling into the system. But we can also do the opposite, tunneling out of the system. If we take out a majority electron and a minority electron creates a spin flip here, you also can create a magnet. And now this is the ordinary ferromagnet, cobalt, and you see 0 bias roughly here is the peak at positive and the dip at negative voltages, and the height are now very different. Looks like second derivative here, so this is inelastic spectroscopy. We, let's say these are ions. Why are the intensities different? Because my tunneling current is still polarized. So you remember, if I have this is a non-polarized tip, this is a magnetic tip. My current is the current from minority current from majority current, and they are not equal because the density states of the sample are different. So actually, this and that process don't have the same current. And to really prove that these are ions, we need a more elaborate experiment we have now. Magnetic tips, we go from parallel to the anti-parallel configuration, and we see that this symmetry in forward and backward tunneling also changes. But we will need that maybe later. These are magnets and films. Are they really magnets? So the easiest way to do it is to go again to an antiferromagnet. Manganese on top of gold. This is again layer-wise antiferromagnet. We have different thicknesses here. And these are the differential conductivity plots now. In an antiferromagnet, we have the same number of minority and majority electrons. So all of the bands are spin degenerate, but fully spin polarized. Yeah, you have an up band and a down band on top of each other, but they live on different atoms. And for four monolayer, you see this peak here, maybe with a little bit of fantasy. Another peak, we go to 6 layers, 1, 2, 8. You see 3 peaks, and dips 10 monolayer again, and so on. And you see that this peak here actually disperses with film thickness. Why? These magnons are confined in this antiferromagnetic field outside this vacuum, and all this non-magnetic system. So we have standing magnons with a number of nodes, 0, 1, 2. So this is a 0 node, this is a 1 node, this is a 2 node node. If we change the thickness, K vector changes here in superposition of plus K and minus K states traveling in Z direction. So just by counting this N, we can reconstruct the Q vector of the magnon, and we have done it here. So this is the momentum, this is the energy. So I take now this energy, this function of momentum that I reconstructed from the standing magnon condition. And certain points, the dotted line is a ab initio calculation for magnons in the system. You see it matches perfectly our observation. And if you don't believe that, you can also say neutron data, but okay, this manganese FCC configuration. FCC manganese does not exist in nature. You have to force it into FCC. This can be done by doping with nickel. So we take manganese dope with 17% of nickel, and then we do neutron diffraction, and you get a black curve for the magnon structure. You see very nicely, okay, we see magnons. Dispersions are listed, the selection rules are correct, everything is fine. So we can see magnons with this here. But maybe you also notice something. If the energy of these peaks is high, they are very broad, and the closer they come to the Fermi energy, the sharper the peaks become. And this is a lifetime of the magnon. And the lifetime of the magnon is different from the electronic states. It depends on energy, and this is called Gilbert damping. So the lifetime of the damping factor is some intrinsic damping plus independent or energy dependent damping. It's linear for antiferromagnets and ferromagnets. And this is our fit. We get a relatively good agreement. So our gamma 1 is about 40 millielectron volts per angstrom, angstrom, and neutron scattering was higher, so the damping was higher, 85, but keep in mind this is 17% doped with nickel, so maybe the damping is also different. So also lifetimes of magnetic excitations can be measured. And even more so, you see that our dispersion does not really stop at 0. So the 0 mode does not live here at 0 energy, it's a bit higher energy. Why is that? So as you know in ferromagnets, the Q equals 0 magnon is a coherent rotation of the magnetization, and it costs maybe anisotropy energy. So there is a spin splitting gap. So the normal magnon spectrum without spin over coupling goes to 0. This is now a ferromagnet, 0, and with spin over direction. Now, so this is the spin orbit direction. The energy I need to rotate the spin. For antiferromagnets, this is a bit different. There's also a gap due to this anisotropy. So E anisotropy is the anisotropy energy, and it goes like square root over this E square. It's exactly like here. But there comes a second term. This is the anisotropy times the exchange. This comes from the fact that an antiferromagnet, two are processing, two spins are processing, and there will be a counting between those two spins when they are processing. Yeah?
So initially you introduced the picture where electrons literally fly into the sample.
Yeah.
So I can think of, let's say, momentum conservation along the surface.
Yeah.
But then you present the data as if EV corresponds to some voltage in a tunneling experiment. So it seems like I cannot think about momentum conservation anymore. So which
Yeah, you have
one
the
of those?
same momentum conservation. So this is a free experiment. You go
Yeah.
from a sample, let's say, above the work function. You go to an electron above the work function. Now with STM, I come in with the electron below the work function, and I end up with the electron below the work function.
Yeah, but then because it's a tip, I no longer have this conservation.
This scattering happens at the electron. So my electron comes into the electron, into the sample. It's a Bloch state then.
Yeah.
And this Bloch state scatters into another Bloch state via energy and momentum and spin exchange. Yeah, is it clear? I'm getting fast here now. Just like before in the phonons, yeah. In the phonons, we had the idea that our molecule can be in the barrier and there's no Q. Your argument is correct. But if I have the phonon inside the metal, then of course, the electron before scattering, the K vector should be the sum of the K vector after scattering plus the phonon.
Yeah, but then basically what I'm saying is that when you do the tunneling experiment,
Yeah.
your momentum conservation is completely broken by the tip itself.
No.
Or no?
This is not correct.
Why?
So, I have my tip, I have my sum, here I have my cross states. At least respective parallel as it one. So this electron will come into this local. So this local state I express as an integral over Bloch states.
Yeah.
Yeah. So I'm not tunneling into a specific Bloch state, but I tunnel basically into all Bloch states.
Whatever Bloch state is allowed by momentum, by energy conservation.
Yes. Then my electron is on the Bloch state.
Yeah.
And my scatter, by full non scattering, it has to go again to another Bloch state. Yeah. So there is an intermediate state here in this process, and the intermediate state is short-lived, so there will be an energy broadening, but the K parallel nevertheless needs to be conserved.
Well, again, then it means that it's conserved up to the broadening of the energy level of this intermediate state, right?
Yeah, the broadening. So this is a state. So how should I draw this? I go to a state.
Yeah.
This state is a Bloch state.
Yes.
It is a certain energy above.
Yeah.
So it has a lifetime which is proportional to 1 over the square. Yeah.
Right.
So that means the dispersion relation I have here, let's say this is a band which is far above Fermi energy. That means I smear this band in energy.
Yep.
So I think more in energy smearing. You could also think on K smearing.
Yeah.
You have to decide for one.
Yeah. Okay.
Yeah, in the formula we either integrate or we've asked this question, is it a function of E or is it a function of K? Can we measure E? Smearing over E. Okay. But these are details. And maybe they are also not so well explained in theory. So actually this theory is not fully, I'm doing the theory partly. Judge Marian does some of it. But important is that there's an intermediate state. Okay, now let's go to magnons. So magnons in antiferromagnets. So there's a processing spin here. There's a processing spin here. But you have to be careful, they are not processing collinear, but they are actually, no, they have opposite rotation sets. So there's an exchange interaction happening. They don't stay parallel. And that means our gap is larger. And this is the energy gap. We measure the function of thickness. And it follows a 1 over thickness rule. So that means we have wide anisotropy and surface anisotropy in this system. That's this side remark. So I'm getting maybe a little bit hard to understand.
So the surface anisotropy is divided by T, and what is T here?
The thickness. So the overall anisotropy density, the volume, is the surface anisotropy divided by the thickness and the volume anisotropy. Volume anisotropy and surface anisotropy, but you distribute it over the volume in principle and effectively. Maybe it's also possible. You have a change of the anisotropy by the surface contribution. If you plot it as function of volume, then the surface will go like 1 over T. Okay. I'll show you something unpublished. Let's go to 2-dimensional Fahrenheit. This is iron germanium telluride. It's a magnetic from glass material. And let me first show you the data. So the bottom is pretty flat. Inelastic time spectroscopy tells us there are a lot of peaks. 0.3, 0.8, 2.3, 3.8, 5.2 million. We can see magnetic domain bonds in this material taking a spin polarized tip. We can measure this inelastic time spectroscopy spin polarized. So if this is a phonon, it doesn't care about the spin of the electron. If this is a magnon, we expect a change of the intensity of these inelastic processes. And that's exactly what we see. So this is a domain here. So this is position, and this is energy, and I color code this. So red means high intensity, blue means low intensity. And you see this peaks here. For example, this one changes in intensity when we go to the main wall, and this one also. So all of the peaks actually change. These magnetic. These must be magnetic peaks, then they change the intensity when you go across the magnetic domain wall. So we know whatever excitation this is of magnetic origin. So it can be magnon. But you can calculate the magnon density of states in this system. It's the red curve. It's completely flat, smooth. There are no special points. There's nothing special about the density of magnons at these energies here. You can think of phonons. Let's assume these are phonons. And then this is the phonon spectrum. So also this does not match. This neither matches the phonon nor the magnon spectrum. What is happening here? And that's something special in two-dimensional systems. And I try to draw it for you. So this is still under review. This work. This is my electron band in 2 dimensions. E. And it's a somewhere is Fermi energy. Here. And I inject an electron above the Fermi energy, somewhere here. So you can relax down to the Fermi level. It changes the energy, but what is Q? I can go to any place here with the same energy difference. So that means I can in principle excite all bosons in this inelastic time process here. There's a transition of boson with small energy arbitrarily. If I stay on the same band, these are phonons. Phonons will show up like that. Phonons, electron-phonon coupled is small like that. It's not a big scattering band. Matrix is small. If you have a ferromagnet, you have 2 bands. Yes. So for spin flip scattering, I have to go with my electron from one band to another band. Yeah. The energy difference is arbitrary, but it will not be at Q equals 0. It's forbidden. And the low energy magnons have Q equals 0. So magnon scattering is not allowed in two dimensions. It's suppressed because I cannot at the same time fulfill energy conservation and momentum conservation. So I expect in my experiment to be blind for magnons. I should only see phonons. But I show these are magnons.
Is this maybe phonon assisted?
Yeah, so the idea is the following. We plotted the magnon dispersion on top of the phonon dispersion. So these are the magnons, right? And phonons calculated by DFT. Magnons are actually neutron scattering data. And you see, oh, they cross. These dispersions cross at 4.9, 1.1, 2.3, 3.6, 5.2, and oh, these are exactly the crossing points. So we have phonons and magnons, but if you distort the lattice, if there's magnetoelastic coupling, you will also change the direction of the spin. So distortion of the lattice changes the local anisotropy, and you can tilt the spin. So that means there's a hybridization happening between magnons and phonons. If the energy and momentum match, there is a forbidden crossing. Yeah.
Why can't it just be a composite process where I first emit some phonon which allows me to dissipate some energy elsewhere and then create?
Yes, you can also think of that image, and I would do the same, but at the same time. You say I create a magnon and a phonon, then we would have a very complicated construction, but maybe possible. But we see these peaks only where the dispersions cross, and that means magnon and phonon have the same Q and the same energy, then it's hard to say what is the magnon and what is the phonon. They are hybridized.
Yeah, but then I can ask what's the signal if I do an unpolarized experiment, right? When I just cite those phonons.
Yes.
And you're saying that if phonons and magnons are hybridized, I won't see any signal.
So this is why we did this experiment. This follows the selection rule of magnons.
Okay.
And in an unpolarized tip, you don't see the magnetic domain, or you see nothing happening. You can still create magnons in your picture, first phonon and magnon, but we don't see that. So we see it only at these hybridization points. And if this is a hybrid object, then you get matrix element for electron-phonon coupling plus the matrix element for electron-magnon coupling to the square. And you get two new terms which enhance this cross-section. This is what we believe at the moment is the correct answer. So Marcus Gast is doing a calculation at the moment to really prove this, but it's my gut feeling that this will be the answer. Anyhow, the experimental observations, these peaks actually are exactly where the crossing points are. And we can apply a magnetic field and shift the magnon dispersion up and down, and you see these peaks moving left and right exactly following these crossings. So we are pretty sure that these are magnopolar bonds. Okay. Let's see if the referee is also okay, there's another effect I want to discuss. That is the Kondo effect. So let's assume we have a non-polarized family, so copper, and we put unpaired electron in a defect. I think most of you are accustomed to the Kondo effect. Then this electron, for example, this electron can hop to a vertical state, or this electron can hop somewhere to a vertical state, and later one of the electrons hop back, and the other one, so actually electron, you exchange this electron with opposite spin direction electron. And this is a virtual process that can happen thermally, in real, or just perturbations, second order perturbation, third order perturbation can happen. And this is the Kondo problem, or it was completely solved by Anderson. So maybe if you think in that way, we have our localized levels, magnetic purity, and since they can hop on and off, they are broadened, virtual broadened, and with this kind of exchange scattering can give me a bound state, or two electron states with two electrons, and they can be attracted. And this gives me a very sharp state at the Fermi energy. This is the Kondo state. It's two electron state. And what this does is actually screening the localized spin of my localized moment by oppositely spin polarized electron, or in the electron you can see, and makes at low enough temperatures, below the Kondo temperature, you have this bound pair silhouette. This nicely sits at the Fermi energy, and you can see it with STM. So this is the first example from the Microscopy. This is cobalt and gold. This is plain gold surface. You see almost constant density of states, and you move your tip on one of these small cobalt atoms, and then you see this wiggling here. And what you should see is a peak, this localized peak at the Fermi energy, but we see wiggles. The answer, the reason that we see this kind of Farmer shape is because it's a discrete state living in a continuum, and we have interference between tunneling from the tip directly to copper, or from the tip into the Kondo cloud into the copper. There are two paths. There's a phase difference, which tune. Depending on the phase difference, this can look like a peak, or this swinging, or a dip. This is a phase argument. So there's an interference of the electron. You can choose two paths to go from the tip to the sun. You can also apply a magnetic field, and this will actually split this singlet and give two peaks. And the splitting is the G factor of 2 typically. And what I want to mention is that now these two, the occupied part of this electron state, will align with the magnetic field, and these pairs are actually 100% spin polarized. If you split the smaller peak, you can make a 100% spin polarized object with localized states. So if you observe this with STM, if you tip spin polarization is full, you only see the occupied one. If you reduce the spin polarization, you can see two peaks. If the spin polarization is 0 of your tip, spin polarization is 0, you see two peaks. And I think the gray one is experimental data, the rest is field. So why am I talking so much about these localized spins? Because I want to go in the direction of superconductivity.
Yeah, I just asked a question. So the conclusion out of this part is just the fact that you showed that you actually can see all that on the experiment quite sharply, and that's the point, right?
Yes, I want to say that if you put a single spin on a Fermi seed, if it's only a single spin, it's not good to think about a fixed single spin, but the Fermi seed will try to screen a spin.
And you still can see it.
And you can see it as a peak at the Fermi energy, or if you apply magnetic field, actually this peak is still polarized.
Yes, okay, good. Okay, thanks.
What is the analogy of this superconductor? Now we split the density of states by the superconducting gap. And there is something similar to a Kondo effect, which is called the Lewis-Gaussian states. They are states, okay, you are an expert, I don't need to explain this. If there's a question, you can there are two solutions to this problem. Either the exchange of my localized spin in contact with superconductor breaks the Cooper pair. And I have now, for example, antiferromagnetic coupling of two electrons here, one localized on my purity, one in the superconductor, or the exchange is weak, and I just keep my Cooper pairs, and they are in some kind of effective magnetic field, which is not enough to break them. So these are two solutions that can happen. Both solutions have an energy. And if I tunnel into this object here, I can excite the system from the ground state to the excited system. Let's say the exchange is small, the ground state is this, and there's an excited state. I break the barrier, cost me delta, but I get the exchange, J, but it's smaller, so this is an excited state. So I can go from here to here, or if I tune J, actually the order of the state of energy is opposite. I can go from the ground state, the large J is exchange, antiferromagnetic alignment, and the excited state is unbroken Hooper pair. So there's an energy which you can excite between those two. This excitation energy is smaller than the superconducting gap. You can live inside the gap. This is an experiment by Wulfhekel, where you have such an electron somewhere, and it's superconducting tunneling, which is superconducting SIS tunneling. So two gaps added on top of each other is this black curve, and inside these two gaps there is this short state, which has the energy epsilon, and this is exactly this excitation energy. Similar to Pongo effect, you can understand this as computational screening and localizing the spin, and it shows up as single particle states in the spectrum inside the superconductor gap. Okay, so we will need that later. But before we go to that, with a localized spin, I want to have many spins, so not water. Many spins. I always press many spins, and I would like to ask if we are close to an antiferromagnetic phase, what will happen if we want to go to the superconducting state? So, of course, there are phonons, can lead to attraction of electrons, but if we are close to an antiferromagnet, we might also create paradiagonals. Yeah.
Sorry, antiferromagnetic stability comes somehow as a surprise. You somehow highlight why.
Why? So why look at cuprates? Cuprates are superconductors, but the parent phase is an antiferromagnet. Or if you look at nuclides, you can do neutron diffraction and neutron scattering, and as a neutron scattering you see you're close to an antiferromagnetic phase, but they are not antiferromagnets. So let's assume you are in a system where the system is close to an antiferromagnet, they have fluctuating spins here, but they are not ordered. And I ask the question, how do two electrons interact? They interact by phonons, but they could in principle also interact by a magnon. So this is paramagnon, it's not strictly so ferromagnet and antiferromagnet, so it's paramagnetic excitation from the ground state to the object with spin 1. And now this screening we have with phonons, so this phone interaction is now in the spin interaction, and my electron self-interacts via magnon emission and absorption, or with scattering, I can think of two electrons, they exchange magnon. The difference with the phonon graph. Sorry, this is but you will see why. I do this. So as for now, is a K minus Q prime but it's non-spin. And if you want to replace this by a button, then of course you have to reverse this spins here. Yeah, then we'll change momentum, energy, and spin on each arm. And this is the graph I'm interested in. And this is actually again the inelastic spectroscopy of that we did before with magnets. Really the experiment we did on these antiferromagnetic layers. What will be the effect for superconductivity? That's a bit complicated now. If we are in a normal state, our magnons are very heavily damped. So we are paramagnetic ground state, we excite on H bar excitations for a short time, they will decay. So what we will get is a very broad spectrum. Now we switch on superconductivity. So before we are non-superconducting, if we are not superconducting, I can spin flip an electron, create a hole in the electron, almost advance strong pair, outer small energy. Now I want superconductor again. So if I want to excite, I have 2 delta for spin flips to fit states. That means my Magnon spectrum, if you like, or my susceptibility function will get of 2 delta. So we're going from the normal state, all the spectral weight will be shifted away and can only start at 2 delta. And the interesting thing is there's a bound state in this gap, which you also can see. Neutron scattering, and it's the long-lived state. Single particle states. So that is something that was also experimentally seen here. I said tonight, unconventional superconductor. You see the magnon was magnetic excitation spectrum, energy resolved. If you go below TC, then you get a black curve, there is this resonance appearing. How would that show up in STM? So let's say we are in a normal state. We have a normal differential conductivity, an elastic one and an inelastic one, which is overdamped magnetic excitation. It's very broad. It looks like a V shape if you do the calculation. That's the experiment. It's a V shaped, just like in theory. Now we switch on superconductivity. Then we need one delta to enter the single particle density states, and to do an inelastic process, we will need another 2 delta. So only at 3 delta, I will have the same inelastic current as I had in the normal state. And below 3 delta, my differential conductivity in the superconducting state should be lower than in the normal state, something very unusual. This is the experiment. You exactly see that coherence peak, differential conductivity goes below what I had in the normal state. And this is a signature that the spectral function, which is related to the pairing of the electrons, actually is heavily renormalized when you go from the normal to the superconducting state. So there are no inelastic excitations except for this resonance below 2 delta. And the interesting thing is that you can take this differential conductivity and fit the DCS part in the lines fit and separate the elastic and the inelastic contribution. So we know the inelastic tonic shifted by one delta, and you can deconvolute that from the get function and you can reconstruct this renormalized bosonic blue function. And this is for iron selenide, and you see the resonance mode here, and you go to the continuum. So that is actually pretty close to what was expected.
How reliable is this data evaluation? It seems to be a very complicated procedure.
Yes, it is a problem because our data is noisy. It's an ill-posed problem. So you cannot strictly deconvolute, but we take a test function, test bosonic spectrum, calculate how our tunneling curve will look like, and then vary it and minimize the error. So if this is the unique answer, I can't tell you, most likely it's not unique. But we get at least this very strong peak. And this mode actually, this resonance mode here, for some reason lies at 1.3 kiloton. And this is also where we find it. So it's at 1.3 delta. Delta is, data is 50 million total concrete precision, 20. That's where it is. But the side remark I want to give is that in this graph, if there's magnon exchange, we flip the spin. So if you think about the order parameter for the superconductor, so if you have a single band, phonons, you scatter from one part without spin flip, so you have an S wave symmetry of the order parameter. And iron selenium has two Fermi surfaces. And you scatter from one band to the other with spin flip. And then the sign of the wave function is inverted. So superconductor's order parameter is S plus minus in this case. Maybe a little bit difficult to understand, but you form pairs which are on different bands and they have opposite spin. The graph you remember, yeah, so this graph, time graph, the spin is replaced but under the scattering process. Okay, I go even more complicated. Forgive me if this is going too difficult, but I only have 90 minutes. Maybe I shouldn't tell this all. Unconventional superconductors for sure cuprates are unconventional. It's not formal mediated superconductor. This is data from business 1.2. Visco, in the normal state, V-shaped differential relativity. In the superconducting state, differential conductivity goes below the normal one. Again, unexpected. It looks again like Magnon's play. Can we deconvolute it as well? The problem is there's only one band. So you have to have a change of the order parameter on the band. That means it must have the zeros. Yeah? So the order parameter needs to change. And somewhere on the Fermi surface, and these are the nodal points. This one is the D wave. So now the electrons that pair the same band, but they are paired in flip scheduling. So we can't have the same sign everywhere, and there must be 0 here. But unfortunately, it means our Dines fit is not so correct. So fitting this with a very complicated function, everything becomes Q dependent. We don't have Q resolution instead. So we average everything by Q. Same argument, deconvolution, and again, what we see is a gap, a peak, a continuum spectrum. So maybe this is also Magnon mediated. This is an assumption. Our theory cannot do better. So our bosonic blue function is not anymore only a function of the energy, but also of Q. And actually delta becomes a function of K. Our theory is not, or our STM measures without resolution for K, so we have to integrate everything, we have to solve everything for every K, add up everything, so the agreement will not be so nice. But at least as a remark, it could be that cuprates are just ordinary BCS superconductors. The boson is among them. Oh, you want this citation? No. Good. Okay. So I'm running out of my voice. I don't know what's the time. Yes. So since this order plays a role here in this school, I will also want to look at this order of superconductors. And the only samples I looked personally are aluminum, which is called granular aluminum. So you go from pure aluminum to oxidized samples, and you basically grow the sample by depositing aluminum with an oxygen back pressure in your chamber. So you will get a mixture of aluminum and aluminum oxide. If there's no oxygen in your pressure, you basically get pure aluminum film. And if you increase oxygen, you have aluminum grains which are separated by aluminum oxide inside. So we start to have grains here already, because as it goes in the crystalline, and then the gray boundaries will be filled with oxygen, and you will decouple those grains. And the experimental observation is that when we do this, so this degree of oxidation can be seen by the normal resistivity of the film. So the more oxide, the more tunnel junctions you have, and the higher is the sheet resistance. If you measure TC, you start with the TC of aluminum around 1 Kelvin, and the more disorder you have, the higher it becomes TC until an optimal value, which is close to the normal resistivity, then it goes. And eventually the system has so much oxygen that these grains decouple, and this turns into an insulator. So this is the superconductor insulator transition. I'm not an expert there, but the interesting thing is that on this side where you have not a lot of oxygen, you follow the relation of the gap and the TC that is given by BCS theory. So this looks like a conventional superconductor, if you like. And if you go above this point, and you become more insulating, delta is much larger than 1.76 kT. So it's not a BCS type superconductor, and the understanding is some authors claim that here the transition to the normal state is not happening by breaking up of the Cooper pairs like BCS, but by boson-Nash condensation. So you have always Cooper pairs, but they become coherent at a lower temperature. So that was also the paper that we discussed on the first lecture, which is still under dispute. So this is under dispute. But we have an SAM we can look at it. So pure aluminum gap is here. We go with oxygen, the gap becomes larger indeed, and still scales correctly. If we go over the optimal point, slightly over the optimal point, the gap is actually maximum. But we see gap states. Where exactly the in-gap states come from. So the only mechanism for in-gap states that I know of is YSR states here. So maybe there are localized states. If you kill superconductivity and measure resistivity of the samples, you will find that there's a condor effect. So as long as you avoid superconductivity, there is a condor effect. And there's a long dispute in the literature why there should be a condor effect. And one school says, I have small grains. There can be an even or odd number of electrons. If there's an odd number of electrons, I have a localized magnetic moment, which makes a local condor effect on my grain. The other solution is my oxide is not stoichiometric. I have dangling bonds, and I have inside the oxygen an unpaired electron, which actually doesn't sit on the grain. Can we distinguish them? This is this experiment. What I do is I measure this Shiba state as function of position. So I plot the spectrum here in color code. Red is high intensity. This is coherence peak, and this pink one is the Shiba states. And if I move over my brain, I see these gets hard, it does not move in energy. So actually with my local gating of the tip, the electric field at the tip, it does not shift in thermal energy. So I will not change the number of electrons. But the YSR state shifts. So I have no electric field here inside the brain, but the YSR state will shift. And this can only mean that these localized spins are in the oxide, where actually the electric field can penetrate. So our belief is that in this oxidation process, we get amorphous aluminum oxide, and there are unpaired electrons there. And if we are separating the grains more and more, we have these localized spins which torque by tunneling to the superconductor and make this magnetic states here. And maybe this is the reason for the coherence of this system. The decay is actually rather big. Jesus Christ, my time is over. So I have more prepared, and I will skip it. But there will be talks in theory of this. YSR bands, entire model, at the end of this tree. It should be Mana state. Yeah? At E equals 0. This is the experiment on Yasani. E equals 0. Wonderful. There is my Mana state, the thing. The latest paper by Wiesenanna, J at equals 0. Wonderful. Here is a Mana state. But you can take another atom and move it to this Mana state. And you see left, right, and left and right, and you have this zero energy state. But if I move this atom on this side, on the left side, nothing changes. I keep my marijuana. On the right side, the marijuana disappears. So it's not a marijuana. So at the moment, this field is completely open. We don't know what is happening. And so I would say the experimental observation is that we need a band inversion. So this is very low chain. And we need a band inversion of these hybridized Shiba states, and maybe this band inversion is never reached. That's maybe at the moment the consensus, but as you didn't have the entire chain yet, it's what's the thing? If you change like the bandwidth of this Shiba bands, you get this inversion, and only for certain parameters you get the marijuana states. And it seems not to be realized so far in nature. That's the end, and I'm over time. Sorry for that, and my voice is gone. So I'm completely exhausted now. Thank you.
Any questions? Can I get the reference to the experiment where one edge state disappeared while
Yes, sure. This reference is here. Nature Communication 14 to last year.
The same question about non-modular story.
The granular aluminum story that I told you that is published in Physical B 2020. Physical B 1 and 2. But I should give the slides anyhow in PDF. I can export it. I don't know to whom should I send the slides. I will export all the slides to PDF so that the students have the slides.
Yes, of course, it would be very useful.
And I send it to you? Or
Yes,
your wife? Or?
yes, you send it to me, and then it will be
Good. Okay. So thank you for all the questions, and I'm sorry that at the end my energy is a little bit low. My battery is expired. Okay.